Hello everyone. In this video we are going to talk about a segmentation technique in image processing called watershed transform. So what is this? This is basically inspired by nature. If you look at the rivers and the valleys that these rivers are flowing inside, you'll see that if there are like several flows of water, several currents flowing through a big valley, then this big valley is kind of divided into smaller valleys, or a smaller, you might call them basin, where each basin, which is like a smaller valley, that basically this water is being drained, or this water is, let's say if it's for farming or anything, it's draining it for agriculture, right? Or if it's nature, then the river might disappear, right? Or if it's like a lake or something, then they're gonna flow into the lake. So these smaller valleys, these smaller basins are separated by some lines, some kind of walls, which here from this picture from Wikipedia, they are called like drainage divide. And another term for them is watershed. So watershed are the ridges, the walls that divide the areas that are drained by different river systems, okay? And each one of these areas, which is separated from the other, and that belongs to one of these rivers, you might call them a catchment basin, or here call it the drainage basin, okay? Which is basically like a reservoir. This is basically the area draining into a river or reservoir. So now what does it have to do with an image? I'll show you. And before I forget, the pictures, text, and equations are taken from 3 resources here. The major one is Digital Image Processing book by Gonzalez, also from MathWork, and from Wikipedia. So if you look at an image, a simple image like this, right, which is a filter, or it might be like from X-ray or whatever, if you look at the image in 3D, the image looks like a topographical map. It has ups and downs, it has valleys, it has peaks, and so on. And so it has some of these local minima, and these basins here are separated by these ridges, which we call them a watershed line. So these catchment basins are separated by the watershed lines, okay? Let me show you for a real image here. So here I have the image, that is the logo of my channel, right? I read it into MATLAB, okay? And here is my MATLAB code, which I'm going to share with you. So it's this first part. I read this EEA ping image, and I create a surf plot for you so you can see what I mean. So this is my image, right? And of course this is like flipped, but if you look here, you see that clearly the image looks like a what? Looks like a bunch of basically basins, a bunch of valleys, in this case deep valleys, that are separated by some lines, right? Yeah. So if you look at it, you might look at it also this way too, from this direction, right? But if you look at it from the top, you can see it like this. Now, if the rain starts to fall onto the system, what happens? If you start filling this object with water, then the first place that the water goes is the deepest hole, right? Is the bottom of those local minima. They start to get filled, okay? So let me show you on this picture here. So if you look at this case or something like that, or this example that I have, so you have something like this, and if water starts to fall down, then the water is gonna what? If it's going all the way, all over the place, not just in one location. So if you start filling it, then the water is gonna fill here, is gonna fill here, is gonna fill here, and here. And they start going up, right? They start going up until what? Until some of these local minima and their basins are filled. For instance, here it keeps going up here. So now this basin here on the left is completely filled. This one on the right, not so. Okay, and these other ones maybe. Now, when you get more water, okay, here, because this guy is filled, now it can overflow into this one. And if that's the case, now this guy starts to come up because this one cannot hold any more water, this basin, so this guy starts to fill up, right? Until now they are kind of even. And that means this one is filled too, okay? So now, if there is more water, they both start coming up, right? Now they have the same chance of getting the water because now they are both filled. But these two are filled, and similarly, these areas too. Let me use a stroke eraser. No. I want a stroke one. I want to see if I can just change this height to something different. So let's say it's this guy here instead. And this one is going to be filled, but this one can go higher, right? And this is how they start these basins to get what? To get filled here, right? This is how they start to get filled at different heights depending on how deep their local minimum is. Okay, so this one is not there. And this is the logic of watershed. It says now this one that is filled, this is one region of the image, this is one region of the image, this is one region, and this is what? One region of the image. So each one of them is a separate blob, is a separate label, is a separate part of the segmentation. Okay? And clearly you can see that the watershed lines, the ridges that are separating them are what here? So you have one here, you have one here, you have one here, right? What are these? Clearly, if you look back at this image, you see that they are the edges. It's the edges of the image that are separating, right? Look at this one here. You see, that's an edge. In 3D, it looks like a sharp hill followed by a deep valley. And what is so special about edges in an image? You are right. How did we detect edges in an image? Using gradient. The gradient at the edges are large. So the method of watershed, as we're going to see, it basically works based on the gradient. So they have what? They have large gradient. These are the watershed lines. Okay, those are the points that we don't even label and we count them as watershed edges. So let's go and take a look at this algorithm here. So first I go and show you applying this watershed to a binary image, because binaries are very easy. Binaries are only black and white, so the only thing you have is 0 and a 1. So you have something like that. Okay, that's the kind of image that you have. This is 0, this is 1, and basically your local minima or local maxima are all the same. They're all at 1. And what we do is we look at the invert of this. We invert it. We apply a not. So we make it like this, basically. So we make the zeros ones, we make the ones 0. So now this is like a local minimum, and this can be, which is equivalent to a white region, this region can be a blob of its own. So we detect the regions of 1 as their own labels or their own basically regions, and we can use it for segmentation here. But one of the things that we do along with the watershed method is a transform called distance transform. So what is distance transform? This is one of the things we typically use along with or before a watershed is applied. We use a distance transform and we convert our image into a modified version of it using a distance transform. This is much easier for the watershed to act on. So what do we do? Here, if we have here, let's say this binary image with a bunch of zeros and ones, the distance transform does what? For any pixel that has a value of 0, it replaces the value of it with what? With the distance of it, the minimum distance of it to the pixels that have a value of 1. So for this 0, the distance it has to a pixel of 1. For this guy, it's a distance of 1. For this guy, it's a distance of square root 2. And so between these, I choose the minimum one, which is 1. So you see this 0 is now being replaced by a 1 here, right? If I look at this, let's say this one. So here it has a neighbor, it has some pixels around it, and this distance for it is square root 2. This distance is 2. This distance is a square root 5. And between these 2, 5, and square root 2, clearly what? The shortest distance is square root 2, which is 1.41, as you can see replaced here. Okay, so for pixels of 0, we replace them with their minimum distance to any pixel with a value of 1. What about pixels of 1? We just replace them with a 0. That's all we do. If a pixel is 1, we just negate them. We just make them 0. That's all we do. Okay? Assuming that we are starting with a binary with a 0 and 1 image. So this is called the distance transform. And in MATLAB, this is done using the command bwdist. So the command bwdist in MATLAB will transform your binary image into a distant image. So if my initial image is this, bwdistance is this guy. And it does make sense because you see that for these pixels of 1, you have a value of 0 clearly, right? They are all black. But the closer you are to the boundaries of these ones, the distance that you have to ones is smaller, so you get darker values. The further away you get from them, your minimum distance gets larger, so you get larger values, so you get brighter. Okay? And this one clearly is not showing us two separate blobs. It's even worse than the original image. So instead of applying the bwdistance command on the binary, we actually applied on the complement of the boundary. So first we make these ones zeros and we make these zeros ones, then we apply the distance transform. If we do that, you get this image. And now this is much easier because now you see clearly what? You see clearly a much narrower structure compared to this binary image, right? These two blobs that have overlap are kind of now separated, as you can see. Okay, and they have their own local maximum here. So this distance transform can kind of separate overlapping blobs for you and kind of distinguish them a little bit better. But since the watershed requires local minima instead of local maxima, so what we do, we apply a negative to this whole image, so maximums become minimums, or maxima become minima, and minima becomes maxima. Now this is good to apply a watershed on. Okay, so you see what we do? We first negate the binary image, we apply a bwdistance or distance transform, and then the result of that distance, we apply a negative to it. Now this is good to apply what? The watershed to. Okay, now this is ready for watershed to tell us that, hey, this is one region, this is another region, and it gives us this wall here as what? As the watershed line, and the rest of it too. So it can break it into two blobs for us. Okay, so for binary image, it's very good. The command to apply watershed algorithm is L equal watershed of an image, and it finds the catchment basins and the watershed lines for you. So it's not or and, it's really. And as I said, the mechanism for it is to treat it like a topographical surface, and it returns a label which tells you which region is which. So in this case, if we apply it, it tells me that, hey, this is basically one region here in cyan color, right? It says this is like L equals 1, and this guy, let's say this is L equals 2. So it gives me two separated regions, and it finds this as that watershed line or the ridge, and it gives me two separate labels, okay? So it returns a label matrix, this command watershed. Now, let me show you the code for this part. So the code is this. I read in that binary image, the one that has two overlap blobs, into my code, and first I show you the image, then I apply the BW distance on the image itself. Next I apply it on the not of the image, right? And finally I show you the negative version of that, which is basically this guy here. So I want to show you these four images, okay? I want to show you these four images. Finally I apply watershed and get this final result here. Okay, so you see here I negated that the BW of not of the image, right? I call it image what not distance not, right? Or negative distance not, you should call it probably. Let's call it negative distance not. Okay, and I show it now. Here I apply the watershed and I get my label matrix L. Okay, and then here I use this command label to RGB. I pass to it the label matrix, and I use what? The jet color map to create this basically colored version of the label images, because I want each label to be colored differently using the jet color map, okay? So I use this new command, label to RGB, which is a beautiful command, right? And you can search it, right? Label to RGB. This is a good command, really good for segmentation purposes, to show your different segmented areas with different colors. This is a beautiful command. You see, it converts a label matrix into an RGB image. So it basically, as you can see, you pass it L, or you pass it L and a C map, which is the color map, and you can also pass it a zero color. Okay, and a zero color, as you can see, is the fill color, the color to fill. And here, if I go back, what is that? That's the color of the background, which is not any of these labels. If you see, the number I passed is 0.5, 0.5, 0.5, which is gray. Okay, so that 3.5s or gray, because if you use all of them 1, that is going to be white, right? But if you just say all of them are 0.5, that means the color to fill the background is what? Gray, and the rest of it, these colors are coming from what? From the jet color map. Okay, so here I create that image and I'll show you that. So let me go ahead and run this section for you. There we go. So this is that image, right? The binary, the BW distance on the binary, which is not as useful, but BW distance on the not of the binary is very useful. And when you negate that, it's ready for the watershed. So now on this guy, I apply what? I apply my watershed algorithm, and I color different labels differently with JetMap, and you get beautiful segmentation here. So you get three areas, the two separated blobs, and the background. So this is a beautiful segmentation, and it could separate these overlapping blobs. Okay. Now this was binary, which is much easier. For grayscale image, we have to look at some different scenario here. So let me, with you, take a look at the grayscale image. In this case, let's say if we look at this image here, which is steel grain. So this is a picture you got from a microscope, and you're looking at the grains of steel, like for your maybe material science class or something, and you want to segment this, right? So the algorithm watershed is applicable to this. The watershed algorithm that could work on grayscale images was first introduced by F. Mayer in 1994, so about 30 years ago. And the way he does it is exactly as I said. He floods basically the local minima successively, right? And then it can form watershed with adjacent catchment basins. Catchment basins are constructed. Now here you do this flooding in what? On the gradient image. So the basins should emerge along what? The edges. And that's exactly what I said up here for you. That's what you really work on are the edges, right? Where have what? Large gradient. So instead of directly applying it to the image itself, you apply it on the gradient of the image. Okay, because if you apply gradient on this image, what happens? So if you apply a gradient, so if this pixel intensities are shown by I, then here is going to be partial of I with respect to X in the I direction and partial of I with respect to Y in the J direction. That's going to be the gradient vector, right? G. And you can look at this magnitude or you can look at the direction. So here you can look at the magnitude of G. And clearly at the edges, you have what? You have very, very large values because you have a sudden drop, right? Or a sudden raise. So at all of these black areas, you have large derivatives, right? At the bottoms, at these valleys, you have zero gradient, right? And then as you go down, you can get what? Bigger gradient. So here, clearly you have some gradient. You have a slope in one direction or in both directions mostly. So if you look at that, then you will get at the valleys, you get a bunch of zeros, right? So here you have like 4 of them. And at those edges, you have what? You have some large values, okay? So you're going to get something like this, okay? And then again, something like that, and something like this, and something like this, something like that, okay? So you apply it on this image, right? And these local maxima, you don't need to label. These are your watershed lines. And you start what? You start labeling all of these other pixels. These pixels you start labeling. So you want to label all of these green ones as one label. You want to go with all of these blue ones as another label. You want to go with all of these black ones as another label. And this is how you want to what? You want to work with watershed. So I just read for you for how this algorithm is explained in simple words. This is from Wikipedia. So it says, a set of pixels where flooding shall start are chosen. Each is given a different label. Okay, so here, all over this gradient magnitude, you go and pick what? You pick some pixels, and you can either manually choose them, so you can manually label, or in this case in MATLAB, here it is automatically chosen. So we take away these points. We are not going to mark them because they do belong to both regions, right? The thing about these watershed lines is, or these edges, that they can belong to both of these basins or they don't belong to any of them, right? So we take them away. We are not going to label them. Now we pick one pixel here, maybe randomly, if we uniformly split a bunch of random points, 1 point there, maybe 1 point here, 1 point there, 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 right? So we pick a bunch of points, and then what? Then we give them a different label first, okay? Now, the neighboring pixels of each marked area are inserted into a priority queue with a priority level corresponding to their gradient magnitude of the pixel. So now that these pixels are given some label, right? Now I go and look at their neighbor. So I look at this neighbor in green, and I look at this blue, and I look at this one in green, and I put both of them to this queue. So if I call this pixel 1 and I call this pixel or 2, and this one pixel 3 and this original one pixel 1, so pixel 2 and pixel 3 are going to go to this queue here, and they go based on their magnitude of gradient. So pixel 2 that has a higher magnitude can go with a higher priority, so being in the beginning of the list depending on how you sort it, right? So if this side is higher priority and this side is the lower priority, so clearly pixels with bigger magnitude will be on the left, or if you do backwards they go on the right, right? So you put them in this queue. Now the pixel with the lowest priority level is extracted from the priority queue. If the neighbors of this extracted pixels have already been labeled, all the same label, then you give the same label of those to this pixel as well. All non-marked neighbors that are not yet in priority queue are put in the priority queue. So now what you do, you come to this priority list, and in this priority list, all of these pixels that we have chosen and gave them a label, they have some neighbors. So these neighbors, they all have been put to there, and maybe among all of these neighbors, this pixel here, if I call it Pn, this Pn with the lowest magnitude of gradient in this priority list, in this queue, it has the lowest of all. So we go after this first, which clearly you see that is closest to the local minimum, right? Or it could be a local minimum. So we go over that and we look at the pixels neighboring that. So we look at the pixel here and a pixel there. And if they both have the same label, so if this is like L of 3 and this guy is L of 3, then we say this guy is also what? L of 3. We give them the same label, right? So this is kind of like filling it with water. And if not, then we bring these pixels around it that are not labeled. So let's say there is one pixel next to this Pn that is not labeled. We grab them and bring them here. So maybe it's pixel Pm. So we bring that pixel Pm that is not labeled, we add it to this queue. And since clearly it has a low magnitude, next or a few iterations after, we're going to go after this pixel too and see how we should label it. Okay, so this way we can get what? We can get to have by growing regions. If one of them got a label, then the neighboring pixels are starting to get the label too, but we don't start from the top. We don't start labeling the pixels on the top of these hills closer to the edges. We start first what? Filling and labeling the pixels at the local minima and their neighbors, and then start growing, okay? So it says redo step 3 until the queue is empty, and the pixels that are the edges that are watershed lines, you don't label them. So in here, basically, if I want to explain that for you, I go all of these black lines, which are edges, you're not going to mark them. So here, if I start with this method, the lowest gradients, like here, maybe here, 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 they get some different labels, and then I start their neighboring pixels, which have a small gradient magnitude, start adding them to the queue and labeling them. So it's like filling this bigger and bigger and bigger and bigger, and the same for this, right? You see? And I keep growing for all of them at the same time. So until they are all starting at their local minima and filling up, I'm not going to grow any of these regions before the other ones. So I make sure that what? I start filling each and every one of them to the same level, starting from 0, filling all of them, right? And once they are all filled, then I raise the bar and now start growing this region. So now I start growing. You see that? So no one of these regions is given a higher priority to what? To any other region. All we do, we bring all the pixels of all these regions to the queue based on their magnitude. And the closer they are to the minimum, they get the higher priority to be labeled first. So that is like, if I go back to this image here, right? Now that is too messed up. Let me see if I can clean it up. Right? So if I go back to this image here, and if you remember, it was something like this, and I don't put a perfect 0 for some of these local minima because they might not be perfect 0 due to noise, okay? So you have something like this. So the idea is this. We start filling, so we draw a line, and anything below this line, we fill it, basically. So we do this. Then, once that level is filled, I go with another level. So now I start filling all of these basins up to this new level now. You see? And then I start raising the bar again. I go up to another level, and I start what? And by filling here, filling is the same as what? Filling of these is the same as for us labeling and adding to the queues. Okay, so it is for us adding to the queue. It's very hard to write beautiful, especially if you want to do it fast. And labeling it. And again, you raise the bar and raise the bar. Now here, when you raise the bar here, these two will be already filled, so you're not going to fill them anymore. They are done. Nothing from these two valleys are going to be added to the queue anymore, so they are done. Okay, because we reached what? We reached a maximum here, and these are those edges that we don't want to label. And we keep going. So this is the essence of this algorithm in simple language. And one of the problems you have with this, with grayscale images, is the problem of over-segmentation. Over-segmentation means the regions that you get from the segmentation are more than the regions probably a human would mark. So here, if you look at these steel grains, this is the result of watershed. If you don't do any pre-processing or anything, you see that the number of grains that this one could detect. So each one of these regions is one separate blob or separate you might call a segmented region. And here you see that these are much smaller compared to these. And the reason for that is noise. The reason for that is the image is noisy. So if you look inside these regions, so this guy should be one region. But what's inside of it? Yes, you got noise. You got noise here. These noises can be detected as edges. So now, if you look at this one, instead of this whole thing being one region, this is detected as its own region. So you can easily break it into two now. Or if these two are a little bit connected too, right, then you can have three regions. Because remember, this operation involves derivative. This guy here is derivative, and derivative is sensitive to noise. If you have noise, the noise will be amplified, and so it will get a large magnitude. And so it will be detected as a ridge, it will be detected as a watershed, and it will be given its own region. Okay? So noise can easily make over-segmentation problem. So what should you do? So here you see it says it occurs because every local minima, even if tiny and insignificant, which means noise, it can form its own catchment basis. So what should you do? You either should pre-process the images. Pre-process means what? Means denoising. You have to get rid of the noise as much as possible and smoothen the image, right? Or what? Or you have to start, once you get this, you have to start merging the neighboring regions based on a similarity criterion. So you might come and say, hey, look, this region and this region are similar in some sense. So since this one is similar to this neighbor region, I'm going to merge them, and I'm saying no, they are not two separate ones. They are actually what? They are actually one single region. So I merge them and I say what? They are one region. Okay, so I have to start merging afterwards or pre-process it. So here I want to show you one technique in MATLAB that was used on MathWork website, and that was a good technique, how you can get rid of it and basically do a better result. So here, this technique, as you can see, could provide very reliable for this image segmentation, and the technique is by suppressing shallow local minima. Okay, so what is this technique? Let me show you. So this technique is what we call H-minima transform, which you can do in MATLAB. The command for it is im H-minima of I and H. What does this command do? So if you pass to it an input image I, or A in this case, and let's say these are the intensity values. In this case, they are really those gradients. But here, let's say this is just any image, and you have a bunch of 10s. You have one region of 7 here and one region of 2 here. So you have two valleys, right? So if you look at it, you have this, and then you have this, you have this, you have this, and then you have this 2, right? And the way, if you look at it from one direction, if I say I am H minimum of A and 4, this 4 is what we call a depth, okay? It's a depth, and anything that is a depth less than 4 will be suppressed. 4 from what? 4 from this base level. So if this base level is 10, I go down by 4, so I reach at a level of 6. Anything that is above the 6, I'll get rid of it. Therefore, this region will be filled and will be suppressed. So only this guy will stay, and you can see that here. Look. Now what happens is that region of 7 is gone, and this region of 2 is not going to be 2 anymore, because now when I fill that, then I brought down my baseline by 4. So now everything is measured from this new blue line. Therefore, this depth that was once, back in time, it was 10 minus 2, 8. Now it is what? It is basically 4, which we went down, plus what it was, 2, right? So it's equal to what? Equal to 6 now. Okay, so this method can suppress some of these shallow minimums which correspond to noise, and therefore it keeps the strong edges, right? So this is the same thing that you do with edge detection also. You also get rid of some noise. You reject some small minima in edge detection too. So here you are removing some of those edges or some of the ridge lines. Therefore, the watershed can only fill a smaller amount of regions. And here you can clearly see that it does a much better job. So if I want to show you how you do it in MATLAB, here I read in the steel grain image, and this is grayscale. And the way that I process this is first I apply IM complement on this. So IM complement is basically converting the hills to valleys and valleys to hills, right? And then I apply the watershed on it. So it gives me the watershed region. And then again, here I need to do something to show the image properly, because when you create this L22, it is not going to be really the result of the watershed is, if you just apply it, let me show you. If you just run this portion, so that's my image, right? If you look at L22, it's U int 8. Okay, and because it's U int 8, if you just show this right away, if you just show this L22 right now, you're not going to see anything nice. So if I say L22 IM show, look, here, you just get a bunch of blacks. Okay, and even you might say, hey, use this, but this is not working because this is for double images. Okay, you still get a bunch of blacks. So you don't see any result of the watershed. So what you need to do is first, also if you look at the result of this watershed here, it has 3 dimensions. Okay, so you want to first convert it to 2 dimensions using RGB to gray, then convert it to double and divide it by the maximum of it. So now the range goes from 0 to 1, and now if you show it, look, you should get some meaningful result. You see, this is that over segmented image. Okay, so you can see that. Now, if you want to do suppressing the local minima, this is the same thing, right? So I still have that image that I read. I use the IM complement of that, but before I apply the watershed, I apply my minimum transform, H-minimum transform with 20%. So I say, get rid of minimas that are not more than 20% deep from the base level. Get rid of them, now apply watershed, and now do convert it to grayscale, make it double between 0 and 1, and show the result. So I've run this for you. Now you get the beautiful result. There we go. Okay. Okay, so this is my code and I'm going to share it with you now. I know there is one line that if you were me, you would pick on that and say, what is this line for? Because I explained everything except for these lines that I said, like L of not image 1 equals 0. What is this that it is doing, right? What this doing is, if you remember, in the case of the binary image, this is my binary image. When I say not of binary image means what? Means this white becomes black, the black becomes white. So not of binary image makes the background that I'm not interested in, make them white. So it says L at those black areas, not of image 1, set them to 0. What does it mean? It means if there is any label in the black area, I'm not interested. Don't go and create a color for them. So get rid of, if there is any label, any blob in the black area, remove it. Ideally, there should not be, but just want to make sure that there is nothing here to work on. So what this one does is to set the pixels that is outside the region of interest to what? To 0. That's what this one does. And here, it basically does a similar thing, except that your image is not what? is not completely binary. It's just black and white here, right? Or grayscale. It's grayscale in this case, sorry, not black and white. And here is basically doing the same thing. Getting rid of, if there is anything in the image that is outside my region of interest, get rid of it. Okay, now in this case you don't. So this is not going to do much for you. But you clearly see that this is the algorithm, and this is the watershed here. So you can have the watershed, and you can also have a connectivity element for how to connect these watershed, because remember we said that we have neighboring elements, right? When we explained this in the beginning, we said that each pixel has a neighboring element. How do you detect connectivity? How do you detect which pixels are neighbors to each other? You can provide that, or you can decide, let MATLAB decide on how the elements are connected together. Okay, so this is what I have for image segmentation using Watershed. Along with it, I showed you the distance transform and the H-minima transform. Hopefully the video was useful to you, and I'll share the MATLAB code under video description so you can download and learn from it. Thank you for your attention. I'll see you in the next lecture.